Hello, everyone, and thanks for joining us. This is Shredder Gym, developed for exercise, nutrition, and more. My name is Michael Roy, a full stack graduate, along with my other two team members that were also full stack app graduates, Cassandra Gross and Tristan Zimmerman. Today, we're going to go ahead and go over our project overview, which is our intro we just finished, our planning, diagram, Terraform, Docker, K8, and more. For our planning to successfully coordinate everything for our project, we relied heavily on GitHub Project to create and organize our tasks. It made our tracking and progress and assigning responsibilities more seamless. For everyday communication, we use Slack, allowing us to quickly discuss ideas, troubleshoot issues, and keep everyone in the loop with real-time updates. When it came to meetings and more in-depth discussions, Zoom was our go-to tool, ensuring we could collaborate effectively when we were working remotely. By using these platforms, we were able to divide tasks efficiently. Tristan took the lead on Docker, Cass managed Terraform, and I focused on some AWS monitoring and overall project coordination. This combination of GitHub projects, Slack, and Zoom not only kept us organized, but also created a collaborative environment. It enabled us to achieve our goals of having a smooth project. It's been a fantastic experience and also very challenging, working together and utilizing these tools to bring our DevOps vision to life. I'm going to go ahead and walk through the architecture for our DevOps cloud infrastructure right now. At the core, we have three main repositories, the DevOps Capstone back, DevOps Capstone front, and the infrastructure, which feed into our CI/CD pipeline. The pipeline handles code checkout, sets up Python environment, builds our Docker images, and pushes them to Docker Hub. From there, we trigger Kubernetes deployments using tools like Terraform. The Kubernetes cluster managed via the EKS on AWS is where the backend services are run, scaling automatically based on demand. AWS infrastructure components, including our VPC for networking and RDS Postgres database for persistence, and EC2 instances for compute power. Monitoring is handled by AWS CloudWatch and SNS for alerting. It provides real-time feedback on the system's health. Additionally, there's robust observability with automated snapshots of EC2 volumes and our RDS database. Ensures that disaster recovery is in place. And also, finally, our Kubernetes manages all deployments, storage classes, pods, and services, integrating them with config maps and secrets to configure our database securely. And now, I'm going to go ahead and pass it over to Cass.
Thank you, Michael. So I'm going to go ahead and talk about Terraform. And Terraform is an example of infrastructure as a code, or IAC for short. And this is a practice in which provisioning, configuration, and management of infrastructure, and this is things such as servers, network, databases, like the Postgres that Michael mentioned, and that this is done through a machine-readable configuration of files and scripts. And this allows us to be able to automate everything instead of having to do this through a manual process. Terraform specifically is an open source tool presented by HashiCorp, and that's allowing us to define and provision our infrastructure as a declarative way. And for our example, one of our infrastructure pieces, as Michael pointed out, is VPC. And this is an example of the virtual private cloud, or VPC, and then along with routing tables and other pieces and the Postgres database, that we can deploy this in an automated manner. These variables that are actually included in the Terraform allows us to be able to use that same code across multiple environments. There are four main commands actually that we use in Terraform, just as an example of how this is helpful in automating everything. We first initialize it. After that, we have a command for Terraform plan, and that shows us what is actually going to post, and then we apply that. And in the end, we can also destroy and completely remove that environment. These four commands and Terraform allow us to be able to recreate this at the push of a button and being fully automated so that we can have our infrastructure out there instantly. And now I'm actually going to turn you over to Tristan, who will talk about Docker.
Hello, everyone. My name is Tristan Zimmerman. We use Docker to package up different portions of the application into portable, lightweight containers called images. These images can be stored on Docker Hub, where they can be pulled back down when needed. This helps eliminate issues related to inconsistencies across machines as the containers are isolated in an isolated environment. For our web application, there are three main Docker images used, one for the Django backend, one for the React frontend, and a third container that helped load some data that is necessary for initial setup. Both the front and backend Docker images are multi-stage builds to ensure that in the end, only what is necessary is kept. This keeps the images lightweight, reducing any errors from unnecessary additions and minimizing the attack surface and dependencies. We use Docker Compose to test out the images locally before trying to move on to further steps such as Kubernetes. Docker Compose allowed us to quickly spin up the entire application with a single command. It uses health checks and depends on to prevent any of the containers starting before a container that it relies on is finished. For our application, this meant that the database starts, a temporary init container loads the initial data into the database, the backend will then start, and finally the front end can start. A network is also added so that all the containers can communicate with one another. At this point, we were ready to move on to Kubernetes. With Kubernetes, we were able to create various pods using the same Docker containers as before, but with many more benefits. Kubernetes allowed us to scale up or down on demand, adding or taking away pods as necessary. It gives our application a healing factor so that if the pod goes down, a new one will start up to replace it, and distributes the incoming traffic across multiple pods to avoid any one pod from getting bogged down. Across our many YAML files, we used probes similar to how we used health checks in Docker Compose, so that a pod can signal when it is started and when it is ready to receive traffic. Config maps and secrets were created to share the necessary configuration information that is needed for the different parts of the application. Service files are used to define how different components or users can communicate with them. The deployment files allow us to say how we want the pods handled, such as how many to deploy, adding probes, what images to use, and provides rolling updates to decrease downtime. Our persistent volume claim and storage class add a layer of data integrity so that if our database were to go down, that data is not lost. We also added a namespace so that this particular application is separate from any other applications that might be running on the same cluster. In order to get the cluster to have access to an initial data load script, we added a special config map that just contained the SQL file. It is only needed on initial startup. An Nginx pod was used in order to direct traffic between the front end and back end, working as a reverse proxy and a load balancer. It listens for requests to the front-end service as well as back-end API requests and routes it accordingly. This separation allows for better traffic organization and improved application performance. To make sure that all these various components worked locally, we first tested them using Minikube. This tool allowed us to run a single node cluster for testing purposes. Once we determined that it was working locally, we made the necessary adjustments to shift the application over to an AWS EKS cluster. These changes include switching the storage class to use AWS EBS volumes and modifying service types to use a load balancer for the external access. And now I will kick it back over to Cassandra to talk about CI/CD.
Thank you, Tristan. So CI/CD stands for continuous integration and continuous deployment or delivery. And the goal here is to automate the process of testing, building, and deploying code. And with the CI/CD pipelines, as they're called, we ensure that every time code is pushed up to our GitHub repository, it automatically is tested, built, and deployed, minimizing human error and speeding up the deployment process. In our project, we're using GitHub Actions, which is an automated tool built into GitHub. With GitHub Actions, we create workflows that automate different processes like the testing of our code or the deploying of our application to AWS, which is the cloud provider in this case. And this ensures that any changes made are instantly deployed to AWS when we have any changes pushed up to our GitHub. The CI/CD files are also in a YAML format, similar to what Kubernetes is with that Tristan mentioned. And we have the file called CI/CD YAML that has file-specific jobs. And then these tasks actually run on GitHub servers and are called steps. And there are specific actions to be taken within those jobs. For example, if we are going to set up the environment where there's like a Python backend and a Node.js front end, we have the dependencies installed properly, and the front end CI/CD will be able to push all of that up and install our dependencies. And since we're using Docker, the pipeline also includes a login step where we use Docker login actions. So it actually takes the images from the Docker files that we have and pushes that up to something called Docker Hub. Likewise, we have a job that brings any new images down, thus further automating the process. And then finally, once these images are built and pushed, we deploy them via Kubernetes or another platform, and in our case, Kubernetes, and using Terraform. So the whole process is automated every time we run code and push it up to the main branch. And now I'm going to turn you back over to Michael.
Yeah, so let's go ahead and go over the AWS services that were pivotal for our project, which included RDS, SNS, and CloudWatch. We chose Amazon RDS for our database needs because it provided a scalable, reliable, and managed relational database solution. It allowed us to focus more on development and less on maintenance. With RDS, you can handle backups, snapshots, and ensure high availability for an application. To keep our team informed and responsive, we integrated Amazon SNS, or Simple Notification Services. SNS enabled us to set up automated notifications for critical events such as deployment successes or failures, and alerting us about any issues in real time. This ensured that we could promptly address any problems and maintain smooth operations. Lastly, CloudWatch was our go-to for monitoring and observability. We set up comprehensive dashboards to track key metrics like CPU usage, memory consumption, and app performance. Additionally, CloudWatch allowed us to configure alarms that would notify us instantly if any metric crossed our defined thresholds, ensuring proactive management of our infrastructure. By leveraging RDS for databases, SNS for effective communication, and CloudWatch for monitoring, our team was able to maintain a highly efficient and resilient DevOps pipeline. These tools not only streamlined our workflow, but they also provide the reliable and good insights needed to deliver a successful project. Next, we're going to go ahead and discuss quickly the tech stack, which the front end was using React and Nginx, the back end with our Postgres SQL database, and what we focused on more of our infrastructure as code, Terraform, AWS for microservices, Docker, and GitHub. And now I'm going to turn it over to Tristan.
So upon getting onto the home page, we're going to navigate up to the login button. We're going to go ahead and sign up with a new user. And after successfully creating our new user, we're going to go ahead and fill out the initial survey. This information is going to give some personalized information like recommended weight range, current BMI, how much water you should drink in a day, how many calories you should be eating, and further implementation to come. Going up to the fitness tab, we can see the pre-built workout programs. This is, I mentioned a few times, having initial data loaded. This is what I was referring to. These programs were hand-selected from various websites and put together so that the user can easily select a full workout program and add it to their specific dashboard. And then going back up to the fitness tab, we can also create our own workouts. So if we just quickly create a chest workout and then go ahead and add that, that should pop up. And then if we go back up to the fitness tab, we can then add exercises to this workout that we just created. And if we type out chest, you can search for exercises based on body parts, specific equipment that you have, or targeted areas. So then we'll just go ahead and pick one that we want, and we're going to add that to the new workout that we just created. And it'll give us a little notification that it was added successfully. In addition to this, there is also a nutrition portion of the code, but we are going to skip over that due to time. Now to talk about some of the hurdles that we went through. A couple of the big trouble areas were getting Terraform and Kubernetes to cooperate. There are a lot of different moving parts, many files. So this took the most effort for the project. Another trouble that we had was just collaborating across different time zones, including different countries. We also uh, this is an evenings and weekend course, so we all had various outside activities besides class to coordinate with. And then specifically getting the initial data into the database was a struggle. When I first created this group project, we had JSON fixtures that were easily loaded manually. So trying to get that working automatically was a struggle. Some future iterations that we would like to consider, maybe adding a AI API that we could use so that the user can get personalized nutrition or workout recommendations, enhancing the graphics of the website, adding performance optimizations just to speed things up and make sure that everything flows very smoothly. Um, Adding an option to export nutrition and exercise history so that you can maintain that data physically. And then possibly adding more suggestions based on that initial server data, like I mentioned at the beginning. And now I turn it over to the audience for any questions.